Good day, folks. Welcome to my YouTube channel. This is the Western Cape Province question paper. It's a September 2024. It's one of the districts in Western Cape. So it says, this is a work energy and power. In Winter Olympics, a skier with a mass of 100, including skates, moves along a race course as shown below. This is the race course, right? Here's the skier there at the top of the height of 300 meters. This is what we need to note. I like this question. It makes life easy. The skier pushes off from the starting point A with a speed of 2 meters. That means the initial velocity of the skier is 2 meters per second as the skier moves down the slope there. At point C, it's the finishing line. So the skier starting line is A, and down the slope passes B to C is the finishing line there. Now, due to the hard and compactness of the surface between points A, B, C, and D, the friction can be neglected over this part of the course. So, from here, from A to D, it's frictionless. This is frictionless, and since it's frictionless, it means it's going to be a closed system because there's no other non-conservative force that is here, so it's going to be a closed system from A to D, right? Now it says the surface between point D and E is purposefully made up of soft compact snow to slow down the skier down before they reach the top of the second slope E. So that means from here to here there is a what? There's a friction, right? There's a friction. So if there's a friction, that means it's an open system. It says due to friction, the skier come to stand to a total standstill at the barrier after they have traveled 50 meters between point E and F. So the displacement there to there is what? Is 50. So also there's a friction there. So from D to F, it's a what? It's an open system because there's a what? There's a friction. There's a friction there. I hope I make sense. Guys, since this is a closed system, that means the mechanical energy here is conserved. The mechanical energy here is conserved. That means the mechanical energy at point A is equal to the mechanical energy at point C. The mechanical energy at B is equal to the mechanical energy at C and also at D. So it's conserved, right? Now it says in 5.1.1, state the principle of conservation of mechanical energy. The principle of conservation of mechanical energy, guys, you need to stick to the exam guideline. It says the total mechanical energy in an isolated system remains what? Constant. Right? 5.1.2, it says determine the total mechanical energy of a skier at point A. So we wanted the mechanical energy there. So guys, here we have a height that is 30 and we have a velocity that is 2 meters per second. That means we do have the mechanical energy there. Now let's calculate that. I'm going to write it here, 5.1.1.2. It says the mechanical energy at A is equal to the kinetic energy plus the gravitational potential energy, which is the kinetic energy, it's half mv initial. The velocity there is initial plus the mg h. So that's the h initial as well. So it's going to be what? The mass is 100 times the velocity is 2 square plus 100, the mass times 9.8, the acceleration times the height, 30. So the answer there is going to be 29,600 joules. That's the mechanical energy at the top that is equal to the mechanical energy at the bottom, there and there, right? Now 5.1.3, it says use the energy principle only to determine the speed of the skier crosses the finishing line. So we wanted the speed of the skier here. So since, guys, from here to here, since there's no friction, There's no friction, so the speed here is going to be constant. So the speed that it gets here is going to be the same speed that it gets there, right? It's going to have the same speed. In fact, all this path is going to be the same speed because it's what? It's constant. There's no other friction, there's no other force, there's no friction as well. So let's write it here. Let's write it here. We're going to say 5.1.3. We'll use the conservation of mechanical energy. I'll use the mechanical energy at point A is equal to the mechanical energy at point B. I'm going to use B. So at the mechanical energy at A, we do have it's 29,600, and the mechanical energy at B is the sum of kinetic energy and the gravitational potential energy. Is going to be half the kinetic energy, mass, times the velocity, which is the final velocity at B square, plus the gravitational potential energy is going to be a mass times 9.8, which is the height at B. There's no height. The height final is what? Is 0. So we're going to times by 0. That is going to be 0. So half times 50 is going to be 50. VF squared, 29,000. And then we divide by 50 both sides. This is going to be 0, guys. And then we can ignore that. So we can might as well. So it's going to be VF is equal to square root, because don't forget to put the square root in there, guys. It's VF squared. So the answer there, it's going to be 24,33. The answer there, 24,33 meter per second. That's the speed for what? For B. And as I told you, that it's going to be the same speed here. It's going to be the same speed all the way up until D, right? So we say the velocity for C is equal to the velocity for B. What is the velocity for B? Is 24,33 meter per second. And at B is gonna be going to the right. Right, let's go to the last question. The last question, it says use the if my reading skills are poor. If the average frictional force on the skier due to the soft snow on the slope between D and E is 300, use the energy principle to determine the skier speed at E. So guys, we are told that the friction here is what? The friction here is 300 newtons. So we wanted the speed that it has when it gets to point E, right? We want the speed at E, but we do have the speed at D. We do have the speed at D. The speed at D is still 24,33. So we wanted the speed there, and this speed, it should be lesser than that. It should be lesser than 24,33 due to the friction, because it's slowing down. 5.2. So I'm going to use the work energy theorem. There I'm gonna say work net is equal to change in EK, and then the work net, what are the forces that are acting? It's very important to ask yourself. The force that is acting here, it's a friction and what? An FG parallel, right? But we don't have the displacement there. We have the height is 5. We do have the height there is 5. We don't have the displacement. We can work that out first. We can say sine what? 45. Sine 45, which is opposite, which is 30. Sorry, which is the opposite. Okay, let me rewrite it. That diagram, it's gonna be that and that. So the height there is 5 meters, and then the angle there is 45. So we are looking for the displacement there. We are looking for that. So we can say sine 45 is equal to opposite over hypotenuse. The opposite is what? It's the height, which is 5 meters, and then the hypotenuse is the displacement. So that means it's going to be the displacement when you cross multiply. The displacement is going to be 5 divided by sine 45. divided by sine 45. So our displacement, when you punch that in the calculator, is going to be 7,07 meters. So that's the displacement there, right? So now we're doing the work net. What is the work net of the forces that are there? It's the work done by friction plus the work done by Fg parallel is equal to change in EK. And then the friction is going to be, work done by friction is going to be Fk change in X cos theta. And the work done by Fg parallel, it's MGH. It's mg sine theta delta x cos theta. And then the change in EK, it's half m v final square minus v initial square. Right, let's look at what we have. We have the friction. Let's use the red. We have the friction, the displacement we have as well, and we have the angle, the mass, then that, and we have the we don't have, so that's what we that's easy that way. Let's substitute. The friction is 300. We're told the displacement is 7.07 cos. The friction is going down the slope as it moves up the slope, so it's cos 180 plus the mass is 100 times 9.8 and sine 45, and the displacement is what? It's 7.07. It's cos. The Fg parallel, work done by Fg parallel, is also going down the slope, is equal to half. And the mass is what? Is 100. And the final velocity is the one that we're looking for. It's the final velocity at E minus the initial velocity is where? It's at D. This is at E and this is at D. Remember at D, I said that the speed when it gets there, it's 24,33 square. Right, guys, when you punch this in the calculator, you punch this entire thing, and then you do the math, your final velocity at E, it's gonna be, should be something lesser than the 24, because it started with the speed here at the bottom of the incline with the 24,33. It should get with something lesser there because there's a friction that slows it down. So the answer here is it's 21,25 meter per second. That's the velocity, guys. There are many ways that you can do this, so many ways, guys. I hope I make sense. Cheers, bye.